Good morning, everybody. I have a pleasure to chair this session. And our first lecturer is Professor Stanisław Krajewski from Institute of Philosophy of Warsaw University. And we depart, fortunately, a little bit from this physics flavor of our conference. And it will be, the title is What Makes the Universal Existential Quantifiers Classical?
Thank you very much. I'm very glad that there's a little bit more than physics here, because that's the domination of physicists is something that is quite impressive, but at the same time difficult for me to follow. Anyway, when we think about the topic, which is becoming classical, we can think, of course, about classical and physics and all those non-classical physics, but also about classical logic and non-classical logics, logical logics actually. And the one general question would be what classical logic is compared or vis-a-vis the non-classical logics. And this is an interesting topic, but this is not the topic I will be speaking on now. By the way, I think it's an interesting challenge to try to characterize classical logic, as much as it is, I think, a good challenge to define what classical physics is. Of course, the easiest way is to say what classical physics is. What it's not relativistic and not quantum, and here it's what is classical logic. It's something that is not non-classical. But of course, it would be nice to have a positive definition, but that's not what I will cover now. I'm going just to consider a special case of the problem of classical logic, or how to see what classical means in this case, namely quantifiers. Quantifiers, generally speaking, are logical counterparts of the general category of expressions, the expressions that express quantity in some broad sense of the term. So we can think about classical and non-classical quantifiers. Maybe it is not the standard term used, but when we think about it for a second, we probably would come to the conclusion that there are those classical quantifiers, which is the universal and existential quantifier, which are well known because they are being, required. The knowledge of them is required from students, I think, of almost all departments, at least in Poland. And but interestingly enough, this is a rather relatively recent concept, historically speaking. Of course, those quantifiers were used in the Aristotelian system in syllogistics, but only in a very limited way. And the general usage of those quantifiers was introduced only in the 19th century. And since then it developed, and it's turned out that this is a very good concept and very good to, in many ways, very useful and very powerful, despite its simplicity. Now, the idea that I want to explore here is that, when we think about those two simple, very simple concepts, the universal and existential quantifiers, what comes to mind is that they are context-free. What I mean is that to understand what the universal quantifier, which means for all, or for every, or all are, means we don't really need to know anything about any specific subject matter. We just have to understand this as a logical concept applying to any possible subject matter. And the same with the existential quantifier. So in this sense, it seems that context is not really relevant, but there are many other quantifiers or quantifier expressions for which context is relevant. So, so the very meaning of all seems to be independent of context. Although, of course, one can be a bit hesitant, because if we think about all, we normally don't think about all objects or all things or all beings in the whole universe. We think about a certain limited area, which is normally given by context. But the very meaning of what all means is independent of context. So context is very important, and many context, in many senses, context is crucial to understand any statement, any expression, almost every that can be given. I would say every expression that is really expressed to convey some meaning. And in this sense, context, I think, deserves to be taken very seriously into consideration, also in logic, but of course also even more in any other area of study. Now, the main idea that I have here is that we can consider context-free notions as special cases in the broader field of context-dependent notions that are of the same category, of the same kind. So here I speak only about quantifiers, but this can be seen as a more general program of seeing how to define context-free or as relatively context-independent notions with respect to other ones. So how does it work with quantifiers? So there are many quantifier expressions. For example, all, always, nowhere, almost never, most, infinitely many, from time to time, a few, quite a few, several, just one, at least one, an overwhelming part of, as many as, roughly as many as, and many, many more. You can imagine that this is. And in mathematics, we have even more specific and more mathematically advanced expressions, like there are finitely many, uncountably, the set of a certain kind is dense in another set, etc., etc. And this last expression is given various precise meanings in various contexts. Anyway, we see that some of those expressions, like all, always, or nowhere, actually they correspond to the universal quantifier, and this is something we can really tell or teach students easily. But there are other ones, like almost never or most. Most is perhaps, well, this is really the point. Most can be defined if we really know if you have the number. So most is more than 1/2, if this is what is meant by most. But most can mean something stronger than just more than 1/2, and then it's another kind of. So what I want to say is that some of those quantifier expressions are clearly context independent. They vary meaning. I mean the meaning, not the application, which is always context dependent. Like always. Always means always. That is in every moment or in every time period or in every situation, etc. But when you say many, it really depends on the situation. Okay, so there are many expressions, as you see, and we can see that there are many quantifiers. If we have a logical concept of a quantifier corresponding to all those expressions of the natural language, we see that we can have many types of many quantifiers. And the universal quantifier and the existential one, which is the dual in the classical case, of course, not in some non-classical logics, but in the classical case, there is at least one, means that it's not the case that all are not. This we can say that these are the classical ones. Well, now, why we would say, I think, properly that they are the classical ones? It's not that clear. Certainly, they are those that are being taught to students. And certainly, they do refer to the Aristotelian usage of it. But the question is, what are the reason to make them so to distinguish them so much as to see them as the quantifiers? For many people, probably, if they have heard anything about quantifiers, they would say that these are the quantifiers and that's it. For logicians who deal with the topic, there are tons of quantifiers. Okay, so why are those general and existential quantifiers distinguished? Those two quantifiers distinguished from among all existing or possible quantifiers? So this is the first question I want to cover. So first, simplicity. Certainly, they are as simple as one can imagine. We can think only about the universal quantifier now because the existential one is the dual, so we don't really need it in this context. So it's the simplest thing. So that's very clear. Then we can say that this corresponds to the important mental operation of generalization. We generalize, that's very important. In many cases we do that, and this is the logical, formal, strict counterpart to that mental operation. Third, interestingly enough, as I already mentioned, the universal quantifier, together with the other elementary logical means, the so-called propositional logic, has a rather impressive expressive power, which is not immediately obvious, but when one gets more into it, then it becomes clear. So of course it's relatively very easy to define something like there are exactly two or things like that. It's more difficult to define some other quantifiers, but still it is sufficient to define quite a lot. So the expressive power is rather strong. When we have the sufficient logical machinery available, but like sets or classes in those traditional systems, like the type theory, etc., then we can define a lot, also very unfamiliar quantifiers, like branching quantifiers, for example, or something like that. Well, perhaps I can say what a branching quantifier is, because I guess it's not something that is generally known. So normally we think about quantifiers as as being put in a linear order somehow, but one also can think about something like this. For all x there is an y, and for all z there is an t, such that some sort of property, say p of x, y, z, t holds, and this is independent of that. I mean, this is independent of that, so we can combine them in a more in a non-linear way. And this is a much more expressive than any linear formula, by the way. This has been known since about 60 years, but of course this also can be converted into a linear formulation by taking this and that separately. So this means that there is a function f, and this means that there is a function g, so that for all x and for all z, we have p of x, f of x, z, G of Z. So this is the way to linearize the branching quantifiers. And this also is a way for me, this example, to show that the expressive power of those simplest quantifiers can be very considerable when we consider things like this. Okay? Then you are not surprised that the expressive power is so considerable. Now, strings of those quantifiers, then we have both now, can measure complexity in a very interesting way. Also, it's interesting to know that Aristotle and later logicians for many centuries never considered nested quantifiers. That is, like quantifier applied to another quantifier applied to another quantifier. This was not considered. And this only brings a lot of complexity and a lot of expressive power, as we can see from here, from the example. So the measure of complexity is very nicely, a certain important measure of complexity is possible using those quantifiers. But, you know, when we think about all those possibilities, it's natural to introduce generalized quantifiers, so-called, and they are formally introduced. It was first done by Andrzej Mostowski in 1957, and then by Lindström and others. And now this is a well-established part of logic. And the definition is the following. So we have a generalized quantifier Q applied to a formula phi is satisfied in a model. Model consists of a set and a certain relations, perhaps functions, etc. If and only if the set of all elements that satisfy phi in the model belongs to the family of subsets of that M, of the universe of the model M, that serves as the interpretation of the quantifier. So each quantifier is semantically defined as a certain family of subsets of the universe. So for each model in which we interpret formulas, linguistic expressions, we have a certain family of subsets of the universe, and this family of subsets is seen as the interpretation of the generalized quantifier. So we can do it in many ways. The universal quantifier, of course, is the quantifier that for each model just has the one element family consisting of the whole universe as the interpretation. Yes, so this quantifier is interpreted as just for each model M, it's the simplest possible. So it's also another expression of its simplicity. And the existential quantifier is the family of all non-empty subsets of M. So this is a very natural generalization. So we can have all other possible families defined, well, how, it's another matter. But that's not all. There is also, so this is called type 1 quantifier. There can be arbitrary, more complicated quantifiers, which were defined by Lindström about 10 years later. And then, we can have several sets, not just family of sets, but the family of the, tuples of consisting of sets. More than that, we can have not only families of sets, but also families of relations, or families of relations, or relations of relations. So it becomes much more complicated, but still it's sort of similar. I don't want to go into those details. It's a bit more complicated, but it's the same general idea. Now, both of them, Mostowski and Lindström, were mathematicians, so they considered this as an obvious part of their definition, that the only quantifiers they considered are only those, say, the family, that way of producing or defining the family of subsets of M for each M should be invariant with respect to isomorphisms. They thought that this is necessary. And of course, from a certain point of view, when we think that what counts is really the number or the size or something like that, then it should be invariant with respect to isomorphisms. But when we think about other quantifier expressions like those I mentioned, many, a few, quite a few, then of course it's rather clear that it should not be invariant with respect to isomorphisms. This is the definition of being invariant with respect to isomorphisms. The isomorphic models have satisfied the same formula, in the same situations and don't satisfy in the same situations. Now, so the others, those other quantifiers seem to be undefinable, or at least not easily definable. So many is simply so context dependent that it shouldn't be defined easily, or perhaps it's not definable. So some people tried a formal definition of many, that we add a variable sigma here and define many as more numerous or equal to sigma, if sigma is a number, or the interpretation of sigma, if sigma is a set, then it's the power of sigma, the cardinality of sigma. You can do that. The problem is that then the interpretation of many and the interpretation of quite a few is exactly the same, formally speaking. But of course, when you think about the meaning of those, they are not the same, right? So that's the problem with those formal definitions. And of course, it's not invariant with respect to isomorphism. The formal definition can be invariant, but the real meaning of many is not invariant, and it's not monotonic. So, for example, let me say what it means. Not monotonic means that we can have that for all x, if phi of x, then psi of x, and still there could be many x such that phi, and not many x's such that psi in a certain situation. For example, when we have, in my class of 20 persons at the university, if we had, 8 students reading books out of 20, and 7 being pregnant, then of course we would say that, many are pregnant and not many read books, right? Even though there are more of those who read than those who are pregnant. So in this sense, it's not monotonic, and it shows that there's also that there's no invariant, they're not invariant with respect to isomorphs. Okay, so because the time is pressing, so let me come to my main point, which is a certain thesis about quantifiers. So what context independence can mean in the case of quantifiers? So one idea is invariance with respect to isomorphisms. This is what we did. The general idea would be that there is no need for any specific knowledge about the world in order to know what the meaning of the quantifier is. Yes, so in this sense it's independent because it doesn't depend on the world. It is purely logical, so to say. Now I want to present a certain thesis, but in order to understand what I mean, we have to understand what a thesis is in this context. So to make it short and clear, this is like Church's thesis, which is pretty well known now, I think, about generally. So this is an attempt to identify two concepts, one more formal and the other more intuitive or informal. And so in the case of Church's thesis, this is the identification or the proposal of to identify the effective, say, effectivity or effective calculability with a certain strict notion like recursive functions or anything like this. And here I would try to propose as an identification of context-independent quantifiers with something more formally defined. Because what context-independent quantifiers are, you know, is not, this is this general idea. No need to have specific knowledge about the word, but this is not a formal sort of approach. Okay, so my main point is really that the quantifier is context-independent if it is definable by the quantifier, the universal quantifier, in some basic logic. By basic logic, I understand the logic like first-order logic or second-order logic or higher-order logic or set theory, which for this purpose can be seen as a general logical framework, or type theory. So any system that can be called logic and does not involve the quantifier. Because, of course, this is a bit subtle, but we can add any quantifier to a logical system and have an enlarged logical system, and that would mean that, of course, that quantifier is definable in that logical system. But the basic logical systems, they just have the universal quantifier, perhaps universal and existential quantifiers. In this sense, they are classical, and they're nothing else. And so the idea is that if it's definable, you know, like this Henkin quantifier is definable in this way or in this way, and this, so if it can be defined within basic logic, this is the definition within basic logic, using the concept of a function, so in a set theoretical framework. So if this is the case, then we can say that this quantifier is context independent because it's definable, and the thesis is that because it's, and if it's context independent, it must be definable. So this is the thesis. The quantifier is any quantifier is context independent if and only if it is definable by the universal quantifier, and in a basic logic, which is like the assumption hidden here in the final formulation. So while those that are definable are clearly can be seen as context independent, the idea that each context independent quantifier is already definable in a basic logic by the universal quantifier is a thesis that really can be justified basically inductively, because we have so many examples. It doesn't seem to have that we can form a quantifier that is in an intuitive sense context independent. It's not definable by the universal quantifier. So this would be the inductive evidence for the thesis. And of course, so briefly, context independence is definability by the universal quantifier. And this, in addition, gives another reason for distinguishing. We had four reasons, remember: simplicity, expressivity, etc. And we have another fifth reason for distinguishing, okay, that it suffices, this universal quantifier, that it is sufficient to define all context-independent quantifiers if we agree that the thesis is correct. So the classical quantifiers are the ones that distinguish context-independent ones among all quantifiers by making it possible to define them, the context-independent, context-free ones, in the framework of classical logic or classical mathematics, for that matter, because set theory is basically the classical mathematics. It defines the classical mathematics. So that's my thesis about classical quantifiers. So quantifiers become classical when they are definable by the simplest, well-known to everybody quantifier for all. Thank you. So, by the way, I published a paper which is called All Quantifiers versus the Quantifier All, and it's available at my academia.edu page, and that's it. Thank you.
Questions?
No, we can, it's the same. Because this is completely independent of that. Because normally when we write, we know that this depends on that, but this depends on those. And here this is independently done, so it's like, yeah. No, but it doesn't matter whether it's, there is an F and there is an G, or there is an G and there is an F, this is the same. No. No, because this is replaced by the existence of a function that for all x's gives y. And this is replaced by the existence of another function that for all z's gives t as g of z. So this is another expression of the same thing. It can be seen by semantical interpretation. Yeah.
No questions? If not, I have a question. Okay, so there is this natural duality between existential and general quantifier. So can you somehow switch this definition and express this in terms of yes?
Yes, I think that it's the same, yeah. Another formulation would be that they are context-independent quantifiers are definable by the existential quantifier. I think that would be exactly the same in the classical framework. Yes, absolutely. Only, I think there are not so many arguments to say that the existential quantifier is so good. I mean, because it's not as simple when it doesn't correspond really very clearly to natural language expressions. Because when we say some, it usually means that there are some that do and there's some that don't. And this is something that is not taken into account in the meaning of the existential quantifier. But still, yeah, formally speaking, of course.
Okay, so let's thank again once more the speaker.
Thank you.
And